For this problem, we want to use the trace-determinant plane to determine the type of phase portrait for two different linear systems, and then go back and actually solve these systems with the general solution to verify that our answer is correct. So for system 1 here, we have the matrix 4 minus 3, 7 minus 6. So our trace is going to be 4 plus minus 6, or negative 2, and our determinant is going to be 4 times negative 6, or minus 24, and then plus 21. So that's negative 3. So because the determinant here is negative, this should be a saddle. Great. For the second system over here, we have a trace of 1 plus negative 5, or negative 4, and a determinant of negative 5 plus 9, which is positive 4. We then want to look at t squared minus 4d. T squared minus 4d is going to be 16 minus 16, or 0. Okay, so here we have a trace of negative 4, and our discriminant here is 0. So the trace is negative, and we're on the d equals t squared over 4 line. This is going to be an improper nodal sink. Improper nodal because we're on the line with the t squared minus 4d equals 0, and a sink because the trace is negative. All right, now let's see if we actually get these out of our general solutions. So for number 1, the determinant of a minus lambda I is going to be 4 minus lambda minus 6 minus lambda plus 21. Lambda squared plus 6 minus 4 is plus 2 lambda, negative 24 plus 21, so minus 3. This is lambda plus 3 lambda minus 1. We can see right now we are in fact going to get a saddle, but the problem wanted a general solution, so let's keep going. For lambda equals negative 3, the matrix becomes, rather a minus lambda I, becomes 7 minus 3, 7 minus 3. Great, they're the same. So an eigenvector here will be 3 and 7. And for lambda equals 1, I will get 3 minus 3, 7 minus 7, which are the same up to multiples. And so a vector here would be 1, 1. And so our general solution for problem 1 will be C1 times 3, 7 for the vector, e to the minus 3t, plus C2, 1, 1, e to the t. And that, in fact, is a saddle, as expected. For number 2 here, we had the matrix 1 minus 3, 3 minus 5. And so in this case, the determinant of a minus lambda I is going to be 1 minus lambda minus 5 minus lambda plus 9. Lambda squared plus 5 minus 1 is plus 4 lambda minus 5 plus 9 is plus 4, which is lambda plus 2 squared. Hence our improper nodal sink, as expected, because we have a repeated eigenvalue at minus 2. For lambda equals minus 2, we're adding 2 to every entry to get a minus lambda I, which will be 3 minus 3, 3 minus 3. So an eigenvector here is 1, 1. Now to find our generalized eigenvector, which I need because I only found one eigenvector here, we know that 3 minus 3, 3 minus 3 times w should equal 1, 1, or 3w1 minus 3w2 equals 1. So for this, I can choose w as the vector, 1/3, 0. Again, many other choices work here, so that my general solution is C1, the eigenvector 1, 1, e to the minus 2t, plus C2, 1, 1, t e to the minus 2t, plus 1/3, 0, e to the minus 2t, which, as expected, is an improper nodal sink. So that is how you can use the trace-determinant plane to analyze what's going on for a system, and then verify it by actually going to find the general solution outright.